Hello and a very warm greetings to respected panel, Professor Madhya, Dr. T. Kimgai and Dr. Ramad bin Talib. My name is Thrisnawathy Anaprapandevan with matrix number AE160087 going to present on my final year project 2 titled Ammonia Detection with No Cladding Optical Fiber, which has been supervised by Professor Madhya, Dr. Noran Azizan bin Cholan. Without further delay, permit me to proceed with the next slide. Water has been one of the vital basic needs for humans, animals and plants. Consumption of quality water is always important in order to maintain a quality life. The problem statement of my project is ammonia is one of the vital pollutants found in water. Excessive amount of ammonia in water could cause contagious effect, such as shortness in breath or even leads towards death. Ammonia detection in water is highly required to be executed. The objectives of my project are to design and simulate an optical fiber sensor based on no cladding PMMA fiber for ammonia detection using beam propagation method. The second objective of my project is to determine suitable wavelength in UV or visible light that has high sensitivity. The scope of my project are optical sensor is designed based on no cladding PMMA fiber using RSoft card software. A suitable light emitting diode or LED wavelength with high sensitivity is determined through simulation. 6 samples of solution with concentration of ammonia varying from low to high is collected in order to carry out experiment. Performance analysis is carried out using the collected water samples in order to determine the wavelength of light that has high sensitivity. My project significance are: apply the concept of no cladding optical fiber into developing optical sensor head, and the developed optical sensor can measure the concentration of ammonia in the solution, and it can provide the information to the user about the ammonia contaminated water. Literature review. Ammonia is a compound that is formed by the covalent bonding of 1 nitrogen atom and 3 hydrogen atom. Human can only taste water with ammonia content less than 0.5 milligram per liter. The ammonia detection method. The first ammonia detection method is titration, which uses the pH scale indicator to determine the chemical substance present in the water, and it detects ammonia in liquid form only. The second method is ion selective electrode or ISE, which detects the ammonia concentration based on the level of hydrogen ion or hydroxyl ion present in it. It can only detect ammonia in aqueous form only. The third method is API freshwater or saltwater test kits. This method is mainly used to detect ammonia in aquarium or fish ponds. It cannot provide accurate or actual data of concentration, as it solely depends on the changes of color on the API test kit. The fourth method is spectrophotometer. Spectrophotometer basically needs some reagent in the form of liquid for ammonia detection, and it detects the concentration of ammonia through spectrum of light. The fifth method is catalytic ammonia sensor, which detects ammonia in gaseous form. The methyl oxide gas sensor, which also detects ammonia in gaseous form. The conductive polymer gas detector, which detects ammonia in gas form, and optical absorption ammonia detection, which involves the interaction of electromagnetic radiation and atoms, and it detects ammonia in gaseous form only. The methodology. My project involved 3 flowcharts. The first flowchart is the flowchart of no cladding optical sensor head designing and simulation. First is to design the no-clad optical fiber by using beam-prop-R software. The simulation parameter setting has been done on the wavelength of light, on the refractive index of core, cladding, and also ammonia. The beam propagation method simulation by varying the wavelength of light and refractive index of ammonia is done. Later, the transmission is seen to be 100% or not 100%. If the transmission of light is not 100%, the design of no cladding optical sensor is being done again. If the transmission is 100%, then we can analyze the simulation monitoring value. The second flowchart is on the beam prop simulation, which involves the first one is to draw the 2D sensor using beam prop simulation, and then set the parameters in global default setting, set the parameters in the properties segment setting, and set the parameters in the pathway monitoring setting. And later, after all the settings are being done, we run the beam prop simulation, and we notice whether there is any error occurring while running the simulation. If an error occurs, we need to go back to the properties of segment setting and check on the setting. If there is no error occurs, we directly go to the data analysis of energy distribution in the sensor. The third flowchart of the project is the overall project flowchart, which involves the designing and simulation of no cladding optical fiber sensor, the energy distribution analysis in the optical fiber sensor that has been designed, the fabrication of no cladding optical fiber sensor, 6 samples with the lowest to the highest ammonia concentration has been collected. The samples are then tested using the fabricated no cladding optical sensor, and at last we analyze the relationship between the sensitivity and ammonia concentration. This is the 2D design of no cladding optical sensor. As we all can see, the cladding region is in green color, the core region is in gray color, the ammonia is in yellow color. This yellow color region is the unclad region, and this unclad region will be the region that will be immersed into the solution of water containing ammonia in order to detect the concentration of ammonia present in the water sample. This is the pathway of light. We basically, in the simulation, we launched 1 milliwatt of light into the pathway to see the energy distribution or the power loss that happens while the light travels through the pathway of light in the core. The next is on the absorbance experimental analysis. The first is involving the measurement of ammonia concentration using the commercial spectrometer to get the real concentration value of the water samples, and then we will do the experimental analysis of absorbance using ocean optics software, which will display the value of photon count or intensity based on the wavelength of light. After that, we will collect and compare the data that is being obtained, and performance analysis of sensitivity is being done. It's the last process of our project. The analysis of absorbance using ocean optics software. Basically what happens is a laptop with the ocean optics software is connected through the spectrometer, the ocean optics spectrometer, and the tungsten halogen light source, in order to make sure that the tungsten halogen is like acting as a light source for the fiber to detect the ammonia concentration. The no clad part is being immersed into the water sample, and the other part of it are outside of the cuvette, and the cuvette is being enclosed so that there is no external sources entering the cuvette while the light is traveling through the core of the fiber. Next is the detection of ammonia concentration using the commercial spectrometer of model AE160087. The parameters used are the cuvette of 1 cm length, the water sample of 1 ml, reagent A of 4 drops and reagent B of 9 ml. The next part is the results and discussion. The parameters used for simulation are the size of no-clad region, which is 20 micrometer, 30 micrometer, 40 micrometer. The refractive index of ammonia are 1.3335, 1.3381 and 1.3440. The value of refractive index has been got from the previous research paper in order to carry on with the simulation. Meanwhile, the wavelength of light that has been used in nanometer are 450, 480, 500, 550, 650 and also 700. The simulation result of graph of power loss versus wavelength. From this graph we can see that as the wavelength increases, the amount of power loss also increases. And also we can also see that when the refractive index of ammonia is n equals to 1.3335, the power loss seems higher than the other two refractive index of n equals to 1.3381 and 1.3440. The same trend happens for the unclad region of 30 micrometer and also 40 micrometer. The refractive index of 1.3335 has the highest part loss or power loss among all the three refractive index. So, from the simulation result, we can summarize that the wavelength of light which has the highest power loss is the most sensitive towards ammonia. As the refractive index of ammonia gets higher, the amount of light passes through the medium decreases. Therefore, the light with 700 nanometer wavelength has the highest sensitivity, hence it has the highest sensitivity towards ammonia. Next is the experimental result using the commercial ammonia meter. 6 samples that has been collected are from G3 lake, RMC lake, pipe water, trench in front UTHM, Carjo trench and also Bestari fish pond. From these we can see that the highest concentration of ammonia is at the trench in front of UTHM. Meanwhile, the lowest concentration of ammonia is the pipe water, which is 0.733. The reading has been taken 3 times in order to make sure the precision of data that has been obtained. The next is the performance analysis that has been done on the experimental setup that has been shown in chapter 3. And from the experimental setup, the graph of intensity against ammonia concentration is obtained. And from here we can see that at the 700 nanometer wavelength, the photon count is the highest. Meanwhile, at the 450 nanometer, the photon count is the lowest. We also can notice the trend that when the concentration of ammonia in the solution increases, the number of photon count decreases along with it. From the graph, we also obtain the linear equation in order to obtain the measured value of ammonia concentration and also to obtain the sensitivity value of all the wavelength of light. The analysis of sensitivity for 450 to 700 nanometer, we can see that the 650 nanometer has the highest sensitivity. Meanwhile, the lowest sensitivity is for the 480 nanometer. From the analysis of sensitivity, we can summarize that the highest sensitivity is obtained at wavelength of 650. The lowest sensitivity is obtained at wavelength 480 nanometer. We can also conclude that The wavelength with highest sensitivity has the highest sensitivity towards ammonia in the water samples. Therefore, wavelength of 650 nanometer will be the maximum wavelength used to detect concentration of ammonia in water. Conclusion and recommendation. The conclusion of this project is the design of optical fiber sensor was successfully created using beam propagation method from the software called RSoftCard, and the wavelength with the highest sensitivity has been successfully analyzed, which is 650 nanometer. The recommendation are the experiment can be conducted using more samples with even higher concentration of ammonia in order to make sure the precision of the chosen LED wavelength. Reagent can be used to improve the value of measured concentration of ammonia, and the development of ammonia spectrometer that is portable can be done. That's all from me. Thank you.